All right, so now let's take a look at another component that we need for SIMS, and those are the mass analyzers. And so we're going to look at a range of these mass analyzers that we have. So the mass analyzer system is, after we've created these secondary ions, we need something to determine what the mass of those ions are so we can determine what elements they correspond to. So as you might imagine, it's composed of multiple components. We have a secondary ion extractor or filter, and then we have the mass analyzer and an ion detector. So the detector, or sorry, let's go in the other direction. So the extractor filter extracts or accelerates the secondary ions from the surface and selects a mass range. So we might actually eliminate some of the ions, and we want to kind of get rid of the primary ions as well, because we only want to look at the secondary. And so it kind of selects for what we want to look at. So then we have the analyzer. And so this is what separates the secondary ions based on their mass charge ratio, m/z. And then the detector counts the number of ions that we have at each specific m/z ratio. All right, so let's kind of go and take a look at one of the terms we just talked about. So I mentioned the m/z ratio, mass over charge ratio. So what does that mean? Think about what the m/z means, and then think about something like argon. And why does argon, so this is a spectrum for argon, why does argon have two of these masses? So brainstorm that a little bit, pause the video, and go to the quiz and see if you can answer that, and come back and we will discuss. All right, so let's take a look at what we're talking about here. So like I mentioned, this is the mass over charge, or m/z ratio. And as the name implies, we're talking about mass, but we have to sort of normalize for the charge. And so we can have a unit charge, so 1, right? So for argon, the atomic weight is 40. And so if we have a single positive charge here, then the mass 40 divided by 1 is going to be 40. However, you can also get argon that's doubly charged, so 2 plus. And so if we take the mass over charge at this point, we still have 40. The mass doesn't change unless you have an isotope, but you're dividing by a positive 2. And so that gives you 20. So that's how we can get multiple masses, because we're talking about mass over charge, not specifically mass. So that's important to realize, because all of the spectrums that you're going to see are going to be m/z. So when we look at this sort of mass spec, you're going to see this m/z ratio, because that's what we're actually measuring, not specifically the mass. All right. So let's actually think about the different ion mass analyzers now that we can have. And I'm going to talk about 3. A magnetic sector analyzer, a quadrupole analyzer, and a time of flight analyzer. We're going to go in more detail, so don't worry about the slide there. So let's focus on the magnetic sector analyzer first. So this selects ion masses, as you might expect from the name, by a magnetic field. So if you can imagine the sample here, we have the primary beam, and then we have secondary ions that are accelerated into this kind of aperture here. And in this kind of box, in this region, we have a magnetic field. So it basically enters the magnetic field. Let's start at the beginning here. So the secondary ions are accelerated with the potential of 4 kilovolts. They enter this magnetic field, and then the magnetic field imposes a force orthogonal to the direction that they're traveling. So we basically get different arcs here. So this is similar to that wine filter that we just saw. And what we do is so these different arcs are caused by different masses. So different mass will result in different force on that those different particles. And so we can basically select the settings of the magnetic field such that only certain masses will go through this aperture or outlet slit into the detector. So we basically select for a specific mass in that case. So we adjust that magnetic field strength, B, so that we select these certain M over Z ratios to go through this exit slit. So that's what the different R's are. So this kind of equation kind of shows you that. So M over Z ratio, that's what we have here. We have the extractor potential here, the magnetic field strength, and then the radius, which is the radius of this sector, this magnetic sector. And so that's what allows us to control. So we can fine tune the magnetic strength and the voltage to select for different M over Z ratios. So the problem here, or the disadvantage of this technique, is that we can only analyze a certain M over Z ratio at a time. So we would basically have to scan through different strengths to record different mass ratios. So that's, it's a slow technique effectively. So let's look at the quadrupole mass analyzer. So what this does is it generates unstable oscillations in the M over Z ions that we are not selecting. So let's kind of look at the diagram here. So again, we have secondary ions accelerated. It's accelerated through the source slit, so an aperture. Then we have quadrupoles, so we have these rods. And you can see here that these two are positively charged, these two are negatively charged electric fields. And that field that's produced in between where the ion's flowing causes either a stable trajectory if the settings are correct for that mass, or in the case of the blue one here, you see that the trajectory, the oscillation, becomes unstable and it goes outside of this quadrupole and doesn't make it to the detector. And so we create this oscillation by these DC and RF voltages that we pair in those cases, and they have opposite voltage, and that's what gives us the trajectory in that case. So again, we're selecting for a specific M over Z ratio, and that results in a stable trajectory and therefore makes it to the exit slit. All right, so let's look at the last one that I mentioned, this time of flight, or TOF, or TOF, sometimes referred to. What this does is it calculates the M over Z ratio based on an ion's flight time, right? Because a certain mass will take a certain amount of time if it's at constant kinetic energy to reach the detector. So it basically, it's a very sophisticated stopwatch, is how I like to think of it. So again, we accelerate the ions. And so in this case, it's a constant kinetic energy of either 3 to 8 in that range of kilovolts. We pulse the ion beam so that we have a certain grouping of ions, and we can time that certain grouping. And so we pulse it from the extractor here, and it goes through the travel path. And so basically, we actually have it kind of out and back. So it basically starts here through these lenses, and then goes to kind of this first stage down here, which causes the ions to turn around and go towards this channel plate detector. So basically, they go out and then come back towards this design. And the time it takes to go from this extractor out here to the retarding voltage and back is timed by the reflecting mirrors, and then going back to the channel plate, the time it takes is translated into mass over charge ratio. So that distance L, in this case that we're using, takes a certain amount of time for given mass ratios. So in these TOF analyzers, heavier elements will take longer flight times, and lighter elements don't take as much time to reach the detector. And here's the equation that basically gives us that flight time. So flight time T is going to be equal to the flight distance L, and then a factor of the accelerating potential, and then the mass. So heavier elements, longer times, lighter elements, shorter times. And so this allows us to calculate what the M over Z ratio is based on the flight time. And so that's kind of the power of this technique. So these TOF analyzers are widely used in the static SIMS technique because they give us a very high resolution, transmission, and sensitivity. So we're able to measure the whole mass spectrum simultaneously for a given pulse. Again, you remember we pulse the beam. Also, since we pulse the beam, the downtime is quite large. So there's in SEM we called it the dead time, right? So similarly, there's a downtime, and this is pretty large, and so we typically isn't great for depth profiling. So if we're continuously producing ions, this isn't the best technique for that.